All right, so solving limits that involve infinity. Notation, again, notation, the way it looks, the first thing you see there is x. As x approaches infinity, that basically means as x moves increasingly far to the right, farther and farther to the right. As x approaches negative infinity, that means as x moves increasingly far to the left. So sometimes be aware that the limit may or may not exist depending on the situation, so be careful on that. So we have two examples right here. What's the limit as x approaches infinity of the function 1 over x? You can see it's graphed over here, 1 over x. So as x approaches infinity, as I keep going, as you can see, the limit for that one is 0. And now what's the limit as x approaches negative infinity? Same kind of idea. As x is getting farther and farther to the left, you see that ends up being the exact same limit of 0. It just happens to be that way for that function 1 over x. Okay, question, is there a horizontal asymptote? Yes, there's a horizontal asymptote. Where is it? Horizontal asymptote is at y equals 0. Well, maybe the horizontal asymptote has something to do with limits to infinity. I'm just saying. Think about that. Keep that in mind. All right, so it says use graphs and tables to find limit as x approaches infinity, as x approaches negative infinity, and then any horizontal asymptote involved of the function sine of 1 over x. You may or may not know what that graph looks like. You probably don't know what that graph looks like, and that's okay. We should go ahead and graph that on the calculator. Then for example number 2, use a graph to find, again without a calculator, the limit as x approaches 3 from the right of that function 1 over the quantity of x minus 3. Alright, so I set up example 2. You can see I drew a little picture of what you would see without a calculator if you think about the function 1 over x, which you just looked at on the previous example. But shifting to the right 3, there I got the vertical asymptote hanging out there. But the one above it, example 1, I graphed on the graphing calculator, and I'm looking at that graph, and you guys might have looked at that graph too on the graphing calculator and said, whoa, that was freaky. So it's hard to draw really what this is. It's almost like comes like this, and it comes down and it goes some freaky deaky thing, and then comes down like that, okay? And then if you notice in your calculator, it's like almost like there's a broken piece, a broken gap right at the y-axis. So, but the thing about this one is they're looking for the limit as x approaches infinity. So going to the right, as x approaches infinity to the right, you hopefully can see that the answer for that is 0. As x approaches infinity, going to the left, so as x approaches negative infinity, that's also 0. Are there any horizontal asymptotes? Yeah, it looks like it, hey? Looks like there's a horizontal asymptote at, again, I'll write it here, HA, horizontal asymptote at, looks like y equals 0. Yeah, for sure. Look at example number 2. It says use graph to find the limit as x approaches 3 from the right of the function 1 over x minus 3. So I graphed our function in blue. You can see there's a vertical asymptote there in green, little green dash line there. So what's happening here? As x approaches 3 from the right, what happened to the curve? You see how the curve is dropping down? So as x approaches 3 from the right, coming from the right, you can see what's happening there. The limit is going to negative infinity. Again, the limit is going to negative infinity. And since it is a one-sided limit, that's the answer you want to put. Now, if it was coming from both directions, if it said limit as x approaches just 3, the limit would not exist. You'd say DNE or does not exist. All right, let's try these two examples. The point they're trying to get at with this, and I'm going to show you how this all works, how basic this is that they're trying to say, look, I don't care how crazy these polynomial functions and rational functions are, like these two are sort of nutty examples. They're saying you can actually find what are called end behaviors, which is what happens when you go to positive infinity or negative infinity, right? What are the end behaviors of the curve without having to put the entire thing in the calculator. Let's say you guys cannot use a graphing calculator for this one, but you got to still tell me what is the what's the limit as x approaches infinity or x approaches negative infinity. Well, if I just can think about the end behavior, again, what's going on, that's all we need. So for this, how does this work? What we're going to be looking for are the highest degrees of each of these parts of the rational function. So like the degree of the numerator is 5, the degree of the denominator is 2, right? So whenever we're talking about end behavior, check it out. I don't need to worry about that part here or this part here. I'm just concerned myself with the first terms of the numerator and denominator to try to come up with an end behavior model. So if we take again, taking the numerator and denominator, think about those. And if I'm saying, look, if I want the end behavior model, I'm going to take this and reduce it as I can. Do you guys see that it becomes 2/3 x cubed? Think about that, 2/3 x cubed. Because, well, 2/3 you can see, but then x to the 5th over x squared reduces to x cubed. So what does the parent function of x cubed look like? Check it out. Now that's not the most beautiful example I could draw, but you get the idea of the blue curve hanging out there. So what are the end behaviors are saying? So as x approaches infinity, looks like the limit doesn't exist because you'd say, well, it's going like to positive infinity, right? As x approaches to the far to the right, then the end behavior would be basically positive infinity. As x approaches to the left, as x approaches negative infinity, the end behavior is again negative infinity, or you'd say DNE because of that, okay? All right, looking at the next one, example B. When they're looking for the end behavior model, once again, we pretty much ignore everything besides the leading terms of both the numerator and denominator. Looking at those leading terms, you can see that the degrees are the same. So if I got to take that as an end behavior model, say, okay, well, 2x cubed over 3x cubed, well, those x cubes, you think about that, they are gone, so literally the end behavior model is 2/3. That's your end behavior model, which means, think about what that is. I don't care how crazy that rational function looks normally, when you graph it out, you'll have a horizontal asymptote at basically at y equals 2/3, so your end behavior, if it's positive infinity, it's 2/3. If it's negative infinity, it's 2/3, as in the limit or the height. So again, 2/3 is just the end behavior model we need. All right, got some more examples here. Woohoo! It says yippee! Anyway, evaluate the following limits. So for these, again, I try not to graph these. Try to picture these. You know, think of the graphs 1 over x, and then shifting, and then picturing what would happen with that. So, first example, what's the limit as x approaches 3 from the right? Well, we're going to have a vertical asymptote at 3, and you got to think of what the graph would look like. So as x approaches 3 from the right, you're going to get an answer of positive infinity. Oh, let's see. The next one. Looks like this is shifted to the left 4. Vertical asymptote there. As x approaches negative 4 from the left. Answer? Negative infinity. And once again, you guys can throw these in the graphing calculator and check it out. So for the third example, even though it has x over x minus 1 instead of 1 over x minus 1, it's still shifting to the right 1. It's just that the horizontal asymptote's not the x-axis anymore. It's just going to be at y equals 1. So it's the same kind of idea. Okay, it's going to look the same. So we're going to say, what is the limit as x approaches 1 from the left? Limit as x approaches 1 from the left, you get negative infinity again. Now for this one, I'm going to zoom in and I'm going to draw a picture of this piecewise graph. But then I want you to be able to try to find these limits logically without even looking at the graph. Think about the end behavior model, think about horizontal asymptotes, maybe vertical asymptote, and see if you can figure out what's going on here. Alright, so I drew the piecewise graph. I guess I just want you to notice that this one here I did in red, and this one here I did in blue. So there's our lovely picture, okay? There's not much beyond that. So let's see. For this function, for these limits, let's see what these questions are asking. First one, find limit as x approaches 0 from the right. Find limit as x approaches 0 from the right. As x approaches 0 from the right, looks like that's going to be positive infinity. The limit as x approaches 0 from the left. Well, limit as x approaches 0 from the left, that is actually going to be at 2. I mean, if you plug and chug and think about what we're going to be using, as x approaches 0 from the left, and I plug in 0 for these x's, here and here, you're going to have basically negative 2 over negative 1, or just 2. So that's why that worked. All right, the next one. Find the limit as x approaches infinity. Find the limit as x approaches infinity. That's going to be 0. And then the last one, final limit as x approaches negative infinity. Now be careful on that one. Final limit as x approaches negative infinity. That would equal 1. Why does it equal 1 for that one? Because, again, if you think about the end behavior model, based off of, again, negative infinity, end behavior model, the horizontal asymptote is literally y equals 1 because the degrees are the same. And that's why. All right. Talk to you later.